Hi, my name is Jeff Goldman with U.S. Army Research Laboratory at Delphi, Maryland. The title of my talk is Gauss Markov Model for Scattering of Acoustic Signals from Rough Surfaces. The motivation for my talk is that soldiers would like to be able to detect and localize elevated targets such as helicopters and UAVs using acoustic arrays. And one of the main paths for the signals going to the array is this indirect path shown in the red, and it's going to bounce off the ground, and the ground is going to have some impact on the signal, and I'd like to be able to incorporate that into the signal processing. Another issue is that you often do not know the type of ground that the array is put on. So it could be in this grassy area as shown here, or the array could be moved over several feet and put into this sandy area. So highly accurate characterization of the ground is not available, which suggests that very simple models may be appropriate. So I am using a very simple model. It's based upon Kirchhoff approximation with an extra simplification. The Kirchhoff model assumes that you have infinite tangent planes for the scatterers. So the angle of incidence equals the angle of reflectance. It also assumes that the first derivative is usually not zero, but is continuous. So I'm making an additional assumption that the first derivative is zero, so that all my red lines here, they all have no derivative. And this really simplifies the calculations and enables you to get some really nice, simple, closed form solutions. So I need to calculate a reflection coefficient. To calculate the reflection coefficient, I need to get a ground impedance, and there are lots of models available to calculate the ground impedance. So two Arduini, Baisley, and others, Keith Attenborough, but there are a bunch. They just need to be, one needs to be picked and applied and you get this reflection coefficient. Another part of the model is that you need a model for the height of the ground. So I'm modeling the height of the ground using two 1D Gauss Markov processes. You can kind of see an example shown below. The Gauss Markov process has two main attributes. One is that if you look at the distribution between different points, it's going to be multivariate Gaussian. And if you calculate the autocorrelation function over a bunch of realizations, it's going to be a decaying exponential function with a based on a constant characteristic length. So what you're seeing here has a characteristic length of 1.5 meters, and the X and Y values are independent. Using these models, you can get closed form solutions for the mean of the reflected or scattered signal and the covariance. So you and they're relatively simple expressions. So if you make some approximations on these expressions, you can get even more insight. So if you assume the ground is relatively smooth, the effect of the ground bounce can be modeled as additive multivariate Gaussian noise. And this really makes life as an algorithm designer a lot easier, because it's very easy to manipulate Gaussian distributions. If the model is not, if the ground is not smooth but rough, then it looks more like multiplicative noise with, again, a multivariate Gaussian distribution. And these results are very similar to the results you see in RF systems with phase noise generated by oscillators. thank you for your attention in this. Any questions? Thank you.